So today it's my turn to start our seminar. This is seminar number 4, and it's a great pleasure to introduce our today's speaker, Professor Jean Freudenburg. So Jean, please.
Thank you, Yvonne, and thanks for helping to organize this nice seminar. I've really enjoyed all the talks so far and look forward to it continuing. Okay, so the title of my talk, Presentations, Embeddings, and Automorphisms of the Homogeneous Spaces for SL2. And this is in a paper that you can find on arXiv if you're interested. All right. There we go. Gotta make sure good. So we want to assume that K is an algebraically closed field of characteristic 0, and in a lot of places I just assume K is equal to C. G is a linear algebraic K group, and V is an irreducible affine G variety. Then it's well known that V admits G-equivariant closed embedding into a finite-dimensional G module. Okay.
I'm very sorry, but at least me, I still see the first slide. Do you suppose that they go for?
I'm sorry. Is that true for everybody?
It's true for me.
Uh-oh.
Maybe to restart somehow.
No, you can choose your PDF and then right, left buttons.
Because I'm sharing and I'm seeing exactly what I want to see. So I'm going to stop sharing for a moment and then hopefully it will come back. Yulia and I worked on this Friday to try to avoid any issues, but apparently there are still issues. Is that now displaying?
Now we see the second slide, not the first one.
Okay, and is it now different?
Yes, yes.
Okay, good. All right, I think it's operating correctly now. Good. Okay, so that's the setup. I'll refer to result of Blankfurter and Polanyi, assuming that we take gamma to be a, excuse me just a minute. There we go. A smooth rational affine curve over C, and G is its automorphism group. Then gamma admits a G-equivariant closed embedding into a G module of dimension 3. Okay, so that's an example. So each of these curves, gamma also admits a closed embedding into the plane. If G is finite and F is G equivariant, then in fact G is a subgroup of GL2. Since every action of a finite group on the plane can be linearized, and those finite groups are of course well known. So the authors of that paper identify curves gamma where the group is finite, but not a subgroup of GL2. So in this case, there couldn't be any G-equivariant closed embedding of gamma in the plane. For example, there exist curves whose automorphism group is the alternating group. Okay. So these kinds of considerations motivate the following two definitions. I say a presentation of our affine variety V with the G action, and the G action is indicated by rho. A presentation of this is an equivariant surjection from the symmetric algebra of the module W to the coordinate ring of our variety V for some G module W, right? And of course, such a thing always exists. Phi is a minimal presentation, I say, if and only if W has minimal dimension. And then the G action on the variety, I say, is absolutely non-extendable if there is no G-equivariant closed algebraic embedding of V into affine space of dimension n, where n is the embedding dimension of the variety, right? So the curves that I described above give examples of absolutely non-extendable group actions. For presentations, notice the condition that G is an algebraic group is necessary. Dirksen, Kuchbauk, and Winkelmann showed that for all n, there does not exist any effective differentiable or holomorphic or algebraic action of the group of automorphisms of the two-dimensional torus on affine space. And of course, we recognize the obstruction here is the presence of that discrete subgroup SL2Z. Yeah, so we really do need to stick with the algebraic groups. The authors construct several examples in that paper of an algebraic group acting on a hypersurface in such a way that the action does not extend to the ambient space. Their methods, notice, only apply to hypersurfaces, and each example they construct is based on a particular embedding of the variety. The notion of absolute non-extendability refers to all possible embeddings of the variety. So I want to begin with two examples for surfaces with embedding dimension 3. And each of these examples is based on the following result due to Kraft and Russell in 2014. Later, I'll give a third example using a surface which is not a hypersurface. So every faithful action of a non-finite complex reductive group on A3 is linearizable. Okay, so for the first example, I want to consider this two-dimensional, the surface C star cross C star, plane with two lines removed, if you like. And of course, I don't want the full automorphism group, given the theorem of Derksen and Kuchbauk, but the subgroup which is the automorphism group of each piece individually. So two copies of O2. Let W be the irreducible O2 module of dimension 2 with weights plus and minus 1. So a very familiar object. And then write two copies of W in coordinates x, y for the first copy and ZW for the second. And then define the G-equivariant surjection by taking the quotient of the two invariants xy minus 1 and ZW minus 1. This is a minimal presentation of the action on V, since there is no faithful representation of G on C3. On the other hand, V does admit closed embeddings in C3. For example, the hypersurface capital XYZ equals 1 is such an embedding. Now, suppose S is a hypersurface isomorphic to V in C3. And suppose further the G action on S extends to all of C3, then by the theorem of the theorem I quoted above, this G action is linear in some system of coordinates and also faithful since it's faithful on S, but this gives a contradiction. So the G action on V is absolutely non-extendable in the sense that I define. For the second example, I want to start with let Wn be the O2 module of dimension 4 defined with weights minus 2, 2, and minus nn, and the sort of natural involution. Okay. So the ideal defined with invariance AB minus 1 and x, by functions AB minus 1 and x plus a to the ny is an invariant ideal. And for each n, we have the quotient isomorphic to the coordinate ring of V, where V is C star cross C. So now it's something a little closer to being a plane, still with units. We obtain a family rho n of faithful O2 actions on that surface, defined by explicitly from the presentation I gave. Right. So anyway, this is what we end up with. Lambda being the element of C star and mu is the involution. The key observation is that this function x plus a to the ny is a variable of the polynomial ring in 4 variables, but it is not an O2 invariant. So it lives in that O2 invariant ideal, but it's not itself an invariant. This yields a sequence of closed embeddings of the surface in C3, which is itself a hyperplane in C4. But that hyperplane is not invariant. So let's suppose that S in C3 is a hypersurface isomorphic to V, and suppose that this action rho n extends to a faithful O2 action on C3. Okay. Then by theorem 4, this action is linear in some system of coordinates. There are 2 types of faithful representations of O2 on C3 given by lambda alpha or lambda beta, where lambda is the C star action, and the 2 different choices for involution are given by these 2 matrices. Okay. If we look at the set of fixed points for alpha, it's a plane, a coordinate plane defined by x equals y. And the set of fixed points for beta is a line given by x equals y and z equals 0. The set of fixed points for the involution mu on our surface consists of the union of a line and an isolated point, so it's a little bit strange. Therefore, rho n can only extend to an action of the first type, lambda alpha. However, since S is a hypersurface, every irreducible component of the intersection of any coordinate plane with S is a curve, thus giving a contradiction. You can't get an isolated fixed point that way. So it follows that for each odd n, the n I use are odd, the action, the O2 action on the surface is absolutely non-extendable, and phi n, the mapping I gave above is a minimal presentation of this action. Okay. So those are 2 examples of these definitions for surfaces. Okay, so with that background, I want to turn my attention to homogeneous SL2 surfaces first, and then after this, I'll talk about threefolds. So in this section, I want to fix the notation where G is SL2. There are exactly 2 homogeneous surfaces for G, which is to say Gx transitively on those surfaces, namely the quotient of G with T and the quotient of G with N, where T is a one-dimensional torus and N is its normalizer in G. And this was the result goes back to an early result of Popov. In particular, we have the coordinate ring of Y is the familiar Danielewski surface given by these 3 generators, and this surface or ring, if you will, has a Z2 action given by sending each of the xi to its opposite. And the ring of invariance is then the coordinate ring of of X given in these in this way. So this is giving that coordinate ring with 6 generators. Okay. 2 observations. First of all, Y and X are both ML surfaces, right? Trivial Makar-Lemanov invariant. And if you like, you can view Y as the complement of the diagonal in P1 cross P1 and X as the complement of a quadric in P2. I don't use those descriptions, but those are nice ways to describe each surface. The automorphism groups of these surfaces were described by Danilov and Gizitulin in the 70s. The standard embedding of Y in C3, of course, is given by xy minus e squared equals 1. And every automorphism of that surface is, in fact, the restriction of an automorphism of the ambient space. That's a result of the description of that automorphism group that they gave. So consequently, notice there can't be any absolutely non-extendable group action on the surface Y. By way of contrast, I show the following. So let rho denote the non-trivial SL2 action on X, which is essentially unique. Then, first of all, any minimal presentation of rho has the form given here k of V4 to the coordinate ring of X, where V4 is the irreducible SL2 module of dimension 5. Second, the embedding dimension of X equals 4. And the SL2 action is absolutely non-extendable, right? So the action is a restriction of a linear action in dimension 5. In other words, I can stick this thing in dimension 4, but not in dimension 3. And regardless of how I put that surface into 4-dimensional space, the SL2 action does not extend. Okay, that's what this says. The proof of part C uses the fact that every algebraic action of a connected semi-simple group on A4 is linearizable. That goes back to a result of Panyushev. So anytime you want to show something's absolutely non-extendable, you have to know something about the ambient automorphism group, of course. All right, so that's a result about this surface X. Of course, Danielewski famously showed that the surface Y is non-cancelative, which is to say that there's another surface Y tilde non-isomorphic to Y, but whose cylinder is isomorphic to the cylinder over Y. Okay. And then I also show that the surface X is non-cancelative. There exists a surface X tilde, not isomorphic to X, but whose cylinder is isomorphic to the cylinder over X. Yeah, let's see. We also construct non-equivalent embeddings of Y into 3 space. And the technique here goes back to a technique that Lucy and I used in our paper on Danielewski surfaces a while back, but we were unable to get this particular case, but now I see how to do it. So the theorem is that we define regular functions in 3 variables in this way. P is xz minus y squared, so we're looking at fibers of P. And I need to use this cubic polynomial f and then polynomial r and another polynomial g defined in this way. So f and g are going to end up being the generators of the kernel of a locally nilpotent derivation and so forth. But without going into those details, every non-zero fiber of P and G is isomorphic to the surface Y. Obviously for P, but not obvious for G. Secondly, every fiber of P is normal, but the zero fiber of G is not normal. And so as a consequence, there can be no algebraic automorphism of A3 that carries the hypersurface, the fiber of, the fiber of, the one fiber of G to the one fiber of P, right? Yeah, so we get these inequivalent embeddings. Okay, so before I talk about homogeneous threefolds, I need to say a little bit about what I call fundamental pairs of locally nilpotent derivations. So a pair of locally nilpotent derivations of an affine K-domain is what I call a fundamental pair if and only if they satisfy these Lie bracket relations, which is to say the Lie algebra that they generate is a copy of little SL2. So that's what I call a fundamental pair. We showed that there's a bijective correspondence between fundamental pairs for the ring and algebraic SL2 actions on that ring, or on the variety that ring defines. So in the paper of Arjantsev and Gaifulen, they showed that if one has a fundamental pair of locally nilpotent derivations in which the bracket of the two is semi-simple, then indeed you get an algebraic SL2 action. So what I managed to do was remove the hypothesis that the bracket is semi-simple. One proves that if I start with a fundamental pair, then automatically the Lie bracket of D and U is semi-simple, right? So that's nice because it means there's much less to verify along the way. Okay, so let DU be a fundamental pair for our ring B, and let capital A be the kernel of the first one, D. Then let E represent the bracket of D and U. That is semi-simple, as I said. And as such, it induces Z gradings of the ring. And the kernel of D, I mean, D and U, of course, are homogeneous. And so A is a graded ring, the kernel. But the important observation is that it's not just Z graded, it's N graded. And in fact, the ring of elements of degree 0 is nothing other than the invariant ring of the SL2 action, right? So I think this is all pretty well known. So if I take a homogeneous element of the kernel, then I write this notation F hat to represent the vector space with the basis given by the powers of U applied to F. I only need powers from 0 to D because we always have the D plus first power going to 0, as in this case. If I let B be another K-domain with another fundamental pair D prime U prime, then of course we're going to say a homomorphism from B prime to B is equivariant if D phi and phi D prime are the same and U phi and U phi prime are the same. So the obvious definition we want to take here, it's equivalent to the SL2 action, or the mapping is equivariant in the standard sense for the SL2 action. All right, so given an n, I want to let Vn, as I did above, represent the irreducible SL2 module of dimension n plus 1 over k. So Vn induces a fundamental pair on the polynomial ring in n plus 1 variables. So I call that, for the moment at least, I'll call that dn-un. And one gives explicitly dn, just sending xi to xi minus 1 and so forth down to x0, which gets sent to 0. And then UN goes the other direction, increases the index, except I have to adjust the coefficients in front to accordingly. So I'm not using the standard representation of binary forms. I'm using something that makes D as simple as possible to work with, because that's my point of view. All right, so we have these standard SL2 actions, linear SL2 actions. So let DU be a fundamental pair on our affine K domain, and let A be its kernel. The following result appears in a recent paper given there with my co-authors. So let A be generate. Of course, A is always finitely generated in this setting, as is well known. So let F1 through FR be a finite set of homogeneous generators. Then B is generated by those vector spaces F1 through FR, okay? And of course, the observation is each one of those vector spaces is SL2 invariant, because it's invariant, each is invariant under both D and U, all right? And so that leads directly to the fact that the equality given there in part A yields a presentation of the SL2 action from these R copies of irreducible SL2 actions, right? And it sends that copy VDI to the vector space Fi. Okay, so that's follows pretty directly. Of course, there are other ways of getting presentations of these actions, highest weight vectors and so forth, but this is tailored to my using fundamental pairs, right? That's what this is about. This lemma represents our strategy, which doesn't rely on Reynolds operators. In other words, to find generators for a ring of invariance B, I want to use known generators for that kernel A. And I'll show you what I mean when I start constructing these examples. But I just want to point that out, that this lemma is sort of the heart of the matter. Okay, so now let's look at homogeneous threefolds. Of course, they're all given by a quotient of H acting on SL2, where H is a finite subgroup of SL2. Okay, these groups have been known for a long time, first classified by Felix Klein in the late 19th century. So the families, the groups or families of groups are, of course, cyclic groups, the binary dihedral groups, which I write BD for n. So the order is 4n, for n at least 2. And then these three individual groups, the binary tetrahedral group BT24, which has 24 elements, the binary octahedral group BO48, and the binary icosahedral group BI20, or 120, I should say. Okay, so this is all quite well known. Each of these groups H acts on the plane, or I would say on the polynomial ring in two variables. And the invariant ring, each invariant ring is generated by 3 elements. Okay, and one Klein gave those generators. And these, as we know, give the various Duval singularity types. All right, so now I want to take coordinates for SL2, natural coordinates, and I want to let H act by right multiplication and let SL2 act by left multiplication, okay? And of course, they commute. So I'm acting on the left by the SL2 action acts on the left. So what I want to do is define the corresponding fundamental pairs. So D acts by left multiplication with the lower triangular nilpotent matrix, and U acts by left multiplying with the upper triangular nilpotent matrix, right? So that gives my fundamental pair, and you can see exactly the effect of those. I want to let A be the kernel of D, which is the polynomial ring in two variables, and B is the coordinate ring of SL2. Then D restricts to the coordinate, the invariant ring of H, precisely because these actions commute, and that is the coordinate ring of the object of the threefold that we want to study. And importantly, the kernel of the restriction of D to BH is the ring of invariance AH. All right. So that sets us up for what I want to do. So by the preceding lemma, I've already observed each AH is generated by three elements, call them R, S, and T. And therefore, the thing I want to understand, BH, is generated by those vector spaces R, S, and T. And that gives us a presentation of the action. Okay. These presentations, however, are certainly not minimal. They tend to include far too many generators. Okay. But we reduce them to get minimal ones. Okay. So that's the strategy. You get a presentation and then reduce it. So here's the main result that I want to present. And I simply give each one of these presentations. So each of the following is a minimal presentation. So number one, for odd integers n at least 3, I get a presentation using the SL2 module Vn. Okay. So in particular, that tells me this coordinate ring is generated by n plus 1 elements. Okay. And I give very specifically what that function is. So the thing to notice is that if remember, xn is the top coordinate of that module Vn. And all I have to do is tell you where the top coordinate goes, because everything else is the image under the locally nilpotent derivation of that guy. So by equivariance, all I have to do is tell you where that top thing goes, and that's it. And it goes to the very simple polynomial z to the n plus w to the n. Okay. For the even n, they split into two types, n congruent to 0 mod 4 or for n equals 2. Then I need a reducible SL2 module, Vn plus V2. And again, the top, if the x's are variables for Vn, and then the y's are variables for V2, then xn goes to Zn plus Wn, but then the y2, the top variable on that side, goes to the product CW. Okay. And that's a minimal presentation. On the other hand, for n congruent to 2 modulo 4 with n at least 6, I also get, as in number 1, a presentation using the irreducible module at Vn, but the mapping is quite different. This was by far the hardest case. It took me a long time to show that the point is that this thing is surjective. That's the hard part, that this mapping is surjective. Okay, so you get everything in that ring of invariance. Okay, and then for the binary dihedral groups, I need the V2n. So mapping to using the mapping to delta n, which is different than the one used above. All right. So again, the rest of these are given by various irreducible SL2 modules, and those are specifically what the functions are. Okay, so each of those is a minimal presentation, and that's that's what we get. So, yeah, I think the best way to, well, talk about these now is by means of these examples. So I'm gonna present 4 examples. So let's start with just Z2, the simplest case, which is the center. We're using the center of SL2, right? And so I'm looking at, according to the theorem I just showed you, BH is generated by these 2 vector spaces, and each vector space is of dimension 3. So there are 6 generators here. I take coordinates for V2 plus V2 in X's and Y's, and the specific function is given by alpha 2 in this way. The ring of invariance on the left-hand side of that picture is well known. It's generated by 3 quadratic polynomials, and it's easy to write them down, but we don't really need to know that. What I want to emphasize is that on the right-hand side of the picture, the ring of invariance of the SL2 action is just the field, right? There are no non-constant invariant functions for those threefolds. So everything on the left in that invariant ring has to get sent to a constant. And we find that the first F1 goes to 4, F2 goes to 0, and F3 goes to -1, at least in the way that I parameterize things. So therefore, the kernel of this map is generated by these 3 polynomials. And the ring of invariance then, as I said, is generated, I'm just spelling out what these 6 generators are here. But it's isomorphic, therefore, to the quotient using that ideal, right? This is a fiber of the quotient map for V2 plus V2, and it gives the coordinate ring, of course, for PSL2, right? So that's the simplest example, right? Let's take Z3. So there the ring of invariance is generated by this polynomial x cubed plus y cubed plus everything that lives above it, right? And coordinates for V3 are given in the x's here. So I get a mapping from KV3 to that coordinate ring that sends x3 to z cubed plus w cubed, all right? The ring of invariance, of course, is generated by the discriminant on the left-hand side, and so that discriminant has to get sent to a constant, and it gets sent to 324 if you in the kind of standard form. So the kernel of this map is that principal ideal. Since H is homogeneous of degree 4, I can ignore 324 and just use 1. And I get BZ3, therefore, generated by these 4 polynomials. And it's isomorphic then to the quotient KV3 modulo H minus 1. And so in particular, that homogeneous space is a hypersurface in C4, right? And it's a fiber of the quotient map for V3. Okay. I want to look next at the quaternion group of 8 elements, BD8. Then according to the theorem, that coordinate ring is generated by these 5 elements. So I want to take coordinates for V4 and X's, and then the map is given in this way. So again, I want to look at the ring of invariance on the left-hand side of that picture, and it's well known. This is generated by a quadratic Q and a cubic R. So we find that Q gets sent to 48 and R gets sent to 0 by this map. So since Q is homogeneous of degree 2, it follows that I can write this invariant ring using these 5 generators, and that is isomorphic to KV4 modulo that ideal Q minus 1 and R. And this again is a fiber of the quotient map for that SL2 module. And then finally, my final example, the binary icosahedral group. And I'm not going to give the same kind of details, but I just want to observe the following. We know that from Klein's list that this invariant ring is given by three polynomials in degrees 12, 20, and 30. So this gives us a presentation according to that lemma. And in that presentation, BH is generated by 12 plus 1 plus 20 plus 1 plus 30 plus 1, which is 65 elements. All right, so you have a very long list of generators if you just take this immediate presentation that you get. But of course, the whole game is to reduce the number of generators. The minimal presentation that I give in that theorem uses the irreducible SL2 module V12 of dimension 13. And so BH is in fact generated by 13 elements. And 13 comes from that R hat, because R has degree 12. So you can throw away S hat and T hat. You just keep R hat, whatever that function is. I give it explicitly, but that's not important here. Okay, so there's some questions I have that I would like to know the answer to. So first of all, I'm going to go back to this surface C star cross C that I gave in one of my first examples. It uses an O2 action, but the involution is this mu, and the mu is that guy that has this funny fixed point set, right? A line and an isolated point. And so a natural question is whether that Z2 action is itself absolutely non-extendable. The obstruction is we don't know about Z2 actions on affine four space, right? We don't have a classification of those. So that's maybe a hard question. I don't know. I'd also like to know what is the Makar-Limanov invariant of this X tilde. So remember, X tilde was this surface not isomorphic to the SL2 surface X, but whose cylinder is isomorphic. The typical or a common way to show the two objects in cancellation are not isomorphic is to show that they have a different Makar-Limanov invariance, perhaps, right? I don't know what that one is. In my proof, I created a different kind of invariant using the plinth ideal, and I could show that those two invariants were different from each other for the two surfaces. But it left open the question of what is that Makar-Limanov invariant? And also related to this surface, can that SL2 action on the surface, which is absolutely non-extendable to four space, can that be extended holomorphically to four space? I don't know. Third question, what are the embedding numbers for these homogeneous SL2 threefolds? I've given minimal presentations, which maybe takes us a little closer to the embedding numbers, but yeah, it's not I mean, for example, for the Z3 action, you have this embedded in C4, and so that clearly is the embedding number for that particular case, but in general, I don't know what these are. And then finally, are minimal presentations unique up to a G module isomorphism, right? It's an obvious question. And again, I thought it was sort of obvious at first that this should be true, but now I'm not sure. Yeah, so that's a question I'd like to know. Okay, so that's everything I wanted to present, and I'd be happy to answer any questions or listen to comments
Many
and so
thanks.
forth.
Many thanks to Jean for his very clear and informative talk. So, dear colleagues, do we have questions or comments, please?
Maybe because observation, this Z2 action defined by t to power -1, t to power ns, the first question, it looks like it comes from the Hirsebruch surface, like an evolution of Hirsebruch surface. Isn't it?
I don't know.
Okay.
I don't know.
Hmm.
I mean, it very well might be. I'm not sure.
And concerning the question which we have on this slide about holomorphic extension of SL2. So this is a lack of my education. So by result of Panyshev, we know that any SL2 action on C4 is linearizable in algebraic category. But other examples of holomorphic but not algebraic action specifically for SL2?
Yes, but maybe not on C4, right? I think Derksen and Kuchbaum gave examples for all algebraic groups, right? Non-linearizable actions, but those dimensions could be quite high in their examples.
And they are really holomorphic. So some, I don't know, difficult functions appear non-polynomial functions in this representation.
Yeah. I don't understand the details for their examples. I just know that they exist. Yeah.
And another question about SL2 over T, this homogeneous smooth quadratic surface. So it has a natural embedding into C3. And as you said, all automorphism of this smooth surface can be extended to the ambient 3 space. So what is your feeling?
Excuse me, but that's for that particular embedding, it's true. For other embeddings, maybe not, right?
So this situation is somehow exceptional. What is your feeling? So usually, if you take some natural naive embedding, the action will not extend to the ambient space. What can be a prediction in general?
I guess I have a different point of view because to me, if you have a natural embedding, the first kinds of automorphism you try to think of are the ones that come from the ambient space. So yeah, I think it's difficult. I mean, I think these automorphisms have to be a little bit exotic to be absolutely non-extendable, but yeah, I don't know. And again, in general, it's all there seem to be many possibilities here. Yeah.
Okay, thank you. Please, more questions.
Could you show us again this X tilde? Maybe I was not paying enough attention. Just because you have this question about its Macaulay-Manoff invariant.
Right, and maybe it's easy to see from a more geometric point of view, but I didn't see it algebraically. Yeah. But I'm sorry, is there a question you had?
I don't remember exactly how it was defined. So
well, I did not define it in this talk. I simply said there exists. But of course, in the preprint, you can look at it's given very explicitly.
Should go into preprint. Okay, thanks.
Yeah. I mean, yeah. It's not overly complicated, but it's complicated enough. Yeah.
Okay, I see. So yeah.
Yeah.
Okay, any more questions? If not, then let us thank the speaker again. So thank you very much.
Thank
And it was-
you.
Thank you.
All right. Look forward to seeing you next month.
Next month, as usual, first Monday, we will have a talk on
Good.
March.
Okay.
Thank you very much.
All right. Thanks again.
Thank you.
Thanks. Bye.